So for the next 25 minutes, we intend just to share with you some of our experiences of bringing together the world of functional safety with the world of operational technology, cybersecurity. If you're not a functional safety expert, you might think, well, why do you want to bring those two topics together? And likewise, if you're a cybersecurity expert, you're thinking, what's the relevance of functional safety to the work that we do? The good news is that if you start to explore the world of functional safety, you'll probably start to realize that the commonalities between the two areas, but importantly, the opportunity to open up some budgets from functional safety to cybersecurity are there for you. So what do we mean by functional safety? Well, as you can see, in combination with cybersecurity, we're very much talking about defending a plant, defending a process, defending an operational system. So if I was running an oil refinery or a processing plant, I personally would want to make sure that I'm safe, but also secure. So combining those two areas is certainly a key part of the work that we've been doing. Now, as you know, within cybersecurity, there are many, many different standards. You've got NIST frameworks, you've got ISO standards. So in working with Jörg, we looked at all various standards that we thought could apply to OT security, and certainly in our experience, IEC 62443 is definitely the standard of our choice when it comes to cybersecurity, simply because it provides a logical, sensible framework for implementing that sort of security model. Of course, key to this is going to be security by design. We've already seen this morning issues around security by design and the importance of doing that. What you're going to be hearing during this presentation is the importance of security by design, but also safety by design as well. So as well as 62443, we've got a standard from functional safety, the world of functional safety, a generic functional safety standard, 61508. Why is that important? Well, it's important for this presentation because if you look at some extracts of 61508, you start to see references directly to the world of security. So now you're having standards that are articulating the fact that you can't really be safe unless you are secure. So again, the two worlds are coming together, and in working with my safety colleagues and safety engineers, developing that messaging and developing services in support of that is certainly key of what we're doing. Underpinning all of the functional safety and cybersecurity work that we do is this great life cycle. Now, very few people actually undertake the life cycle in its entirety, or will start developing products and will go through the process line by line, because this is really an ideal world. But ideally, this is the life cycle that we would suggest you look at when designing processes or systems. And you'll notice that there is good similarity between 61508 and 62443. So as a cybersecurity person, as an OT security person, I hope to get involved very early in the design phase by looking at the risks and the threats and doing risk and threat analysis. Likewise, my colleagues within the world of functional safety will be doing similar work around designing in the functional safety message. The great thing about functional safety, and Jörg will always tell me this, is that he can guarantee that a system is safe because they have the SIL factors, so they can prove deterministically that a system is safe. In our world, in OT security, we have to be a bit more vague when it comes to the security levels that we apply to appropriate systems and processes, but we're working hard to try and make that happen. So this is the typical life cycle process that we would adhere to. What we'd like to do now is hand over to Jörg, and we're going to focus down on some very specific areas about designing software safely and securely, and the V model.
Thank you, Nigel. My name is Jörg Krämer. I'm coming from the functional safety technology, and functional safety means the system have to be safe, otherwise it could be that people could die. And the developers of functional safety devices needs a standard which explains on which way they have to develop the software. And in the 61508, we have that we model. And now our customers, our developers of these safety systems ask us, what we have to do now for cybersecurity. Is there a we model in the standard, in the 62443? No, it isn't, but we thought we can do that. The 62443 is structured on that way, this part 4-1 and 4-2, that we can build this we model. And now we have to merge this we model to our 61508 model, because the message is, it is not more work to do cybersecurity in a functional safety development. You have to do that in the same time. You can do that. Often you have the same measures to detect or to avoid some faults. And here we start with the specification of the safety requirements and the security requirements. Later on, in the next 3 steps, we have to do secure by design, as safe by design. The coding means we have to implement our source code, and the right branch here means we have to test that. And that means here we have to do a module verification, and the last step then is the verification and validation of the complete system. Yes, to explain that, I have a short use case for you. A very simple thing. Here, this customer wants to program his PLC via a USB memory stick. There is no network on the PLC, and in the past they had a special memory. This was owned, manufactured by this company, and now they think, okay, we can use USB. That is more hip and trendy, yeah? I don't know. But now we want to use that. And he asked us, is there a problem with that according to cybersecurity? Do we have threats about that? And we ask what you want to do. Yes, we want to bring our program, the application program, to each of that PLCs, and that PLCs we want to use for robots to build a robot cell. Okay, I discussed that with my colleagues, and I said, okay, we have to start normally with a specification. Requirement specification, you see here, we have the starting point as R in this we model. And in this specification, what we need for functional safety, we can insert now cybersecurity points also. For instance, functional safety means the safety function. If the door will be opened, the robot has to stop. That is a safety function. Otherwise, people could die. Yeah? It has to work, really. Here for cybersecurity now, we have an additional requirement. That means we want to program this PLC via this memory stick, and we want to fulfill a security level 2. So now we have SIL 3 security level 2. After this specification phase, normally the developers start to think about what could happen. In functional safety, it calls FMEA, the failure mode effect analysis, to find out what could happen. We could have an under voltage detection, over voltage defect, or we could have an endless loop and something like that. For the cybersecurity, you know that calls threat modeling, and here we have that use case. That means we have the USB port as an entry point. We have the data flow to the CPU, and from the CPU to the memory. And according to that, for instance, Microsoft Stride model, we have for each of that points, data flow entry point, PLC, and memory, we have some threats. And these threats we implement now in our FMEA. And that is what our customer wants to hear, to know. Because they're coming from functional safety, they know what an FMEA is, so we have to talk in the same language. That is much easier for them to understand what they have to do. And here, we start with this table and we see we have for functional safety, we have to detect some random faults. And the random fault in the data flow could be that the message is corrupted, that the telegram is not complete, and normally for that we use checksums, typically a CRC 32 checksum or something like that. On the other hand, now we have to think about cybersecurity, and here we have STRIDE. That means, for instance, tampering or information disclosure. Tampering is going in the same direction like this message corruption. That means we need a checksum, but a bit better than this typical CRC checksum, for instance, a hash code, MD5 or something like that. Information disclosure is a special which is only for cybersecurity. Later on, we see here cable break that could happen for functional safety. It could also happen for cybersecurity. How you have to handle that, you need a fallback scenario. And next point here, we have to detect some faults in the CPU. You have some RAM faults, you have some internal flag faults because of bits which are tipping, because of soft errors, yes, and you have to detect that for functional safety. What happens then? If you detect such a fault, the system has to go to the safe state. That means the robot stops. And here we have to do that also for cybersecurity. Then it calls tampering, and it could be that something is changed. And you can use here the same measures to detect that. So sometimes you have to make better measures for cybersecurity. For instance, not only the CRC 16 or 32, you need a better checksum like a hash code. Sometimes you need an additional measure, but sometimes you can use the same measures to achieve your goal, to make the system safe and secure. You start then with the concept. And typically in functional safety, we start with the hardware concept. And typically in that hardware concept, you have for ZIL3 a dual channel system. Dual channel system means you have two inputs, two CPUs, two outputs, and each input and each output is compared in that CPUs. If one CPU is defect, the system goes to the safe state. Now we have to make the software concept. In the software concept, we will find some functional safety points and cybersecurity points. We start here with the first requirement, the safety function. Later on, in the programming, you can find that that these requirements, which are named there, are used for both, for functional safety and cybersecurity. And later on, you see here some hardware tests, the dynamic tests from RAM, ROM, flags, and so forth. So with that concept, we can go to build an architecture. And architecture means here what is different between a standard software and a safety software. A standard software, the architecture is really easy. In safety software, you have to make a good separation between the standard and the safety software. It cannot be that the change in the standard software have any influence to safety software. For instance, if you want to use a standard software on your PLC, like an operating system, take care that this PLC software, this standard software have no influence to your safety function. But the point is, standard software often will be patched, but more often secure software will be patched. That is necessary because In functional safety, you will have, over the complete lifetime of your machine, the same risk. And this risk you have to reduce. For that, you need special measures to detect some faults and in the development to avoid some faults. But now here we need patches, because one day it could be that your encryption is not good enough. Then you have to patch the system. And now you have this additional view to this architecture. Now you need a separation not only between the standard software and the safety software, you need also a separation between standard software, security software, and safety software. It cannot be if you change something, doing patches in your secure software, that you change the safety function. For instance, that the robot switched off too slow. I have here a small example, only one aspect according to that. Here you see the PLC, you see on the left-hand side the microcontroller, you have the RAM cells, you have special RAM for the standard data, and you have this RAM cell for safe and secure data. What you're doing is you write directly your program via USB through the microcontroller in that safe memory. That is an application program. What could happen? It could be that this message is corrupted, that the telegram is defect, that one bit was tipping, and you can detect that with your checksum. On the other hand, it could be that another guy wants to read the code directly from that PLC to change something, perhaps. Or he wants to know how does it works to make a copy. So for tampering, we have the checksum, but for this information disclosure, we need a bit more. What Ali talked about, we need then a good encryption. That is then an additional requirement for these developers. So after this design phase, we start to implement that, and the implementation standard, yes, we have to use good coding guidelines. For functional safety, we used all the time the coding guideline MISRA from the automotive guys. Yes, now we have these cybersecurity standards, and we use the cybersecurity coding standard, for instance, that functions always only used which have a buffer check, buffer length check, something like that. And we're doing directly after this code writing, we're doing the static analysis. Static analysis is not that what the compiler normally is doing, it is a bit more. For instance, a data flow anomaly analysis. That this here cannot happen. Some compiler can do that. Sometimes you need a better tool for that. And you can calculate a cyclomatic number, which is the complexity of your software. We know that from Ali, that is a control flow graph. You have here 3 instructions, and you have 2 ways through the complete software. The first way is here directly from beginning to the end. The other way is with that small loop. And McCabe say nothing more than this. Is McCabe 2, that means you have 2 ways through your software. And that means you need minimum 2 tests to check that your software is working. And you have to do code review to find faults early, to find some misunderstanding early. That is the typical way to do that with the code review. Then we are here in the right branch of this V model, and we have to test the software. And to show you what I mean, I have here a small example, a very easy and complete senseless program, I know. X is equal 1. If x greater equal 1, do this, a loop. Otherwise, jump directly to x equal y. So what we want to do is we want to check with all these code coverage tests each line of code and each branch of code, and that we want to avoid, to achieve. So here, the first jump is directly in the loop. We find a fault. Yeah, this x is equal 1 that we have detected, and we can see we need additional instruction or additional test. So what we can find is we can find some errors, we can find some backdoors, for instance, from the developer, yes, and we can find some Easter eggs. It cannot be in functional safety that there is one line of code which is not tested. And that you have to show, to document with their tools. For instance, LDR, testbed, TESI, Cantata, something like that. The last step here, after all that module tests, and we have to know for each requirement, we have to build a test. And after that, you know each line of code is tested. Otherwise, you have to see why it is not tested. Is it because it is an Easter egg, or is it because of we have not specified a test? The last step here is the integration and system test validation. Then we check the complete system. We put in manipulated programs which not fit to the checksum, for instance. We check the boundary, maximum program, minimum program. We use defected USB memory sticks, for instance, we have an internal shortcut to see how does it work, what happens. Thank you.
Thank you, Jörg. So, as you can see, the worlds of functional safety and OT cybersecurity are very much starting to come together. It's a journey that we're all on, but the good thing is that the standards are now starting to endorse the work that we're doing here. So, if I were you sitting there working within a process plant or an OT facility, I'd be thinking, what does this mean for me? I'd be thinking, well, go speak with your functional safety colleagues. Go speak with the safety people within the process plant. Understand how they work and understand how you can resonate with them to ensure that they are safe by being, quotes, cyber secure. I think ultimately we talk about safety and security by design. I know it's a bit of a cliche, but certainly in our view, you certainly cannot be safe if you're not secure. Maybe you can't be secure if you're not safe. So that's it from us. I hope you've enjoyed it.
Okay, we have some time for questions here.
Thank you very much. Hi, Gary Williams. I'm the cybersecurity lead for process automation within Schneider Electric. Love the presentation, but what I wanted to add is that if you follow the SDLA, the ISA Secure Development Lifecycle Assurance, which encompasses embedded device testing, align with the functional safety 61508, the addition to para 8 now says risk and threat assessment should go. The fact that we've aligned those two together answers the question here is that how do we move forward? And it is a combination of both the safety 61508, 61511, as well as the IEC 62443. But the secure development lifecycle and the embedded device security assurance, so on the image that you showed, the way that we've separated the safety from or reduced the risk to the safety from the cybersecurity element is we've EDSA certified the communications module, and then we're using triple modular redundancy on our Triconic system, and therefore you can update the software without increasing the risk to the safety system.
So I think in summary, what you're saying is this is correct, which is great. But you sort of taken maybe a slightly different approach to that with what you're doing. So maybe we should catch up a bit later. It'd be really interesting to speak with you. Are you on the standards bodies as well?
I'm one of the board members for the ISCI.
I thought you might have been, so let's catch up later. But yeah, very good, thank you.
Thank you very much.
Other questions? So you mentioned quite a bit IEC 62443, and they have a partner organization, ISCI, with their ISA secure standards and such. Do you see, if we're relying so much on 62443 to guide us in security, do you see the certifications that body is going to come up with as the driving certifications, or do you expect there to be a number of certifications related to security and control systems?
We doing the cybersecurity certification together directly with the 61508, and I think that will be in the future will be typically. All our customers ask us now for beginning a new project to start directly with the 61508 and the 62443, and the 62443 is more or less that what the 61508 is in the moment. For functional safety is the 62443 for cybersecurity. I'm not sure have a complete answer to your answer or question.
No, I guess as I would interpret that answer is that you expect there to be multiple certifications. Yeah. Because the ISA Secure is actually coming up with tests and certifications that then will be various bodies will do, but there's a number of different, the approach you mentioned is a different approach to that. So it sounds like you think there will be a couple of different approaches.
So we are accredited not only from the DAX, German accreditation company, also from ISA Secure. So we can do the complete certification according that what the ISA Secure requires also.
Okay. Okay, we have time for one more question over here.
Ayman Alisa, Chief Technologist of Industrial Cybersecurity with Booz Allen Hamilton in the MENA region. I'm very furious when we talk about certification for cyber. I understand that we can certify the functional safety part of the system, but when we talk about certifying cyber part, I get really very annoyed hearing this. Especially that, for example, there could be vulnerabilities that are not known in any system, and they are discovered after years. It takes people sometimes many years to discover a vulnerability. So how can we say that a system is certified from cyber perspective while this part is impossible in my humble opinion? Okay. What I advise is that we don't even use the word certification. We use the word tests, or something that has been completed, or this system has been tested against those controls or those functions, and it certifies, this is what we certify. But the word itself, certification, sometimes could be misleading.
So can I start? Mm-hmm. So you're absolutely correct, and this is something that I'm personally very passionate about, and we have discussions because Jörg can say that he can mathematically prove deterministically that a system is safe. I can't prove it's secure. All I can possibly do is say, in a point in time, it meets the requirements of a security standard, but I absolutely cannot say this is secure, and no one can. So I think security driven by certification is dangerous, but the reality is that we do need a context, we do need something to measure a security level against. So 62443 has a number of security levels. They're quite vague, and achieving the higher security levels, almost guaranteeing yourself against a nation-state attack, I think is pretty tough and be very, very expensive. So I absolutely agree with what you say, and I'm careful in the language that I use when I'm talking about this to executives who are demanding certification. I have to caveat my response. don't know if you've got anything to add to that.
Yeah, a very important point is also how is the patch management later on working. Yes, and that is quite new for functional safety topic also. You never change your running system if it is functional safe, but now you have to change. Patch management is a very important point later on. What we can do in the development is that it doesn't matter what you change in your cybersecurity part, that it has not an influence to safety. That means if something influence is there, the machine, the process will stop.
Okay, thank you, Nigel and Jörg. Thank you very much.